So this is the day one problem of perfect squares. And the instructions say that we can use the digits 1 through 9, at most one time each, to fill in the boxes to make each expression evaluate to a perfect square number. So, for example, if I use the number 5 in the first expression, that has to result in a perfect square. But before we begin, let's just recap what a perfect square is. So a perfect square is the product of an integer multiplied by itself. For example, 100 is a perfect square because it's the result of 10 times 10. They're both identical. 36 is a perfect square because it's the result of 6 times 6. Both the factors are identical. Now I could also express this 6 here and that 6 there. I could break those down into their prime factorization to 2 times 3 times 2 times 3. So I've expressed 6 a little differently as 2 times 3, but again, identical. So to do this problem, I could go through and use trial and error. And if you tried that, you can definitely get the right answers, but it's not very efficient. And we don't want to waste time. We want to be as efficient as possible. So I believe that using prime factorization would be the most efficient way. So I'm going to use prime factorization to help me answer the problem. What I'm going to start by doing, though, is I'm going to write out on the side the digits 1 through 9 and how they can be expressed in prime factorization. So 1 is 1 times 1. 2 is 1 times 2. 3 is 1 times 3. 4 is 2 times 2. 5 is 1 times 5. 6 is 2 times 3. 7 is 1 times 7. 8 is 2 times 2 times 2. And 9 is 3 times 3. So I'm going to use the prime factorizations of the digits that we're allowed to use to help me create identical factors to create a perfect square. So let's look at 18 times some number times 2. Well, 18 can be rewritten as 2 times 3 times 3. 2 times 3 is 9. 9 times 3 is 18. 2 can be written as 1 times 2, but multiplying by 1 doesn't change the value. So I'm just going to keep the 2 here. And if I try to create two identical factors with just the numbers that I have a 2 and a 2. So I'm going to put one on the left, one on the right. I also have a 3 and a 3. One on the left, one on the right. So far they're identical, but we still need to pick a number for the box. So I'm going to go through the list of digits I'm allowed to use. I'm going to see which ones that I could place in here that will keep both sides, both factors identical. So I'll start with 1. 1 is 1 times 1, and that I could definitely use. If I place a 1 on the left factor and 1 on the right factor, both sides remain identical, and that would end up being 6 times 6. So 36 would be the perfect square created if I used 1 as the digit. So I'm just going to put a 1 in here in the box. Let's see if there's any other ones we could use. Two wouldn't work because I'd end up with 1 and 2. So that's not going to work. They're not identical. 3 wouldn't work for the same reason, but 4 could work. I'll end up with 2 times 2 on each side. So left factor, right factor identical. That's 12 times 12, which is 144. There's another perfect square. So 4 is an option. Let's see what else there is. finally, I think the last one that I can use is 9. 3 times 3. Left factor and right factor identical. That would be 18 times 18, which is 324. So 9 is also a possibility. So I can only use each of the digits 1 through 9 once. So if I pick 1 to go in the box right here, if I pick 1 to go in that box, I can't use it again in any of the other boxes left in the problem. So I'm going to leave the 1, 4, and the 9 there for now. And then what we would do is we'd use this approach for the rest of the problems, and we'd see which numbers can work there, and then we can decide which number we use. And that's it. That's how we would solve the problem.